Welcome to I Can Science That, where we do honest investigations of everyday science. If you're aware of the channel, you may know that flat earthers are welcome here, and we often investigate the ideas of flat earth and take an honest look at what's going on there. I've been wanting to talk about 8 inches per mile squared for some time, and tonight is finally the night I'm going to get around to it. Today's video is a little different than most. Today's video is specifically targeted not at the flat earth folks, but at the globers out there in the audience, and hopefully to teach some of you some things you might not already know. That's always fun, because we here on the side of science, which of course all globers are on the side of science, love learning new things. Many of you already know this, but I know for certain some of you do not. For any of you flat earthers out there, you might want to stick around to the end as well, because today's topic is all about when the flat earthers get it right. So if you've ever investigated the concept of flat earth, you have certainly heard 8 inches per mile squared. Many times I've heard from flat earthers, that's what NASA says. That's the supposed curvature according to you guys. No, that's not our number. That's not our formula. That formula, as near as I can tell, is something that was made popular by Samuel Rowbotham, who was a famous flat earther. This is not the equation that NASA uses. This is not the equation that you find on Metabunk. This is not what any of us use. I was never taught 8 inches per mile squared. The first time I ever heard of this was in the context of the flat earth discussion. But now that I am aware of 8 inches per mile squared, let me tell you what it is. It is an approximation, and it is an approximation for the drop rate. So according to the spherical model of the Earth, of course, if you went on a straight line, if you looked along a straight line out away from a point, a level point, took a straight out from there, the curvature of the Earth, of course, according to the spherical model, drops, and the rate of drop over distance can be approximated as 8 inches per mile squared. So what more is there to say? Turns out there's a lot more to say on this topic. And what I really want to do is catch the attention of anyone who is in the debunking community, anyone who is a glober, who's out there fighting the good fight to put the smack down on those flatties, right? If you're out there trying to dunk on flatties, then this video is for you. What I'm going to do in this video is I'm going to derive the actual formula for the drop rate, the formula that NASA would actually use, not Rowbotham's formula. The 8 inches per mile squared is Rowbotham's approximation. We're going to go through the actual. And we're going to discover it's not just one formula. It's going to get complicated because I'm going to show you 4. I'm going to show 4 different formulas of how to get this number. And then we'll compare those correct formulas against this approximation, and we're going to see how good does it hold up. And then finally, there at the end, I will try to sum up why I'm here talking to you about this, why I find this so important. And yeah, spoiler alert, it's not about the results. The results are interesting. Please do check it out. Check out these results. I think they'll be eye-opening, particularly for the debunkers out there. I think you'll find this enlightening. But there's something even more important than just that. Warning! Warning! The following slides contain math. I am about to derive the formulas for the drop rate according to the spherical model of the Earth. If you don't want to see trigonometry, you don't want to see algebra, you're going to want to avert your eyes and maybe skip ahead to the comparison part. I will put down in the description, I will put jump links so that you can jump ahead to the wrap-up part where we see the results. The math is intended for that globe fan audience who wants to know more and wants to be enlightened about more discoveries. And also, I have a bit of an ulterior motive, which is, as we'll see in a bit, it has been suggested that I cannot do math. And so I'm just going to defend myself a little bit by showing you some math. As always, if I make any errors in my math, please do come here and leave a comment, and I will highlight your comment and I will pin your comment. I will make the correction and post a new video because that's what this is all about. It's about learning, getting better, and improving your own personal knowledge base by clearing out the false facts and filling in the true facts. As I mentioned before, we're about to discover that there's more than one way to measure this distance. And the reason for that is because in a globe model, there are multiple different ways to measure distance. Let's show a little diagram here so I can explain what I'm talking about. This curve is a section of the spherical Earth. Over here, we have the value that we will be looking for, which is the drop height. So I'm using H for drop height. This is the amount of distance that is different between if the Earth was flat across the top and if the Earth were curved along this line. That difference we will call the drop height. And you will notice I have defined it to be perpendicular to the original level, not perpendicular down here at the point of intersection. Across the top, I will call this distance L. This is the distance that you would get just in the straight line distance. If the Earth was flat, then the distance out to this point would be the same as the distance to this point, right? And so if we just shot a straight line parallel to the surface at the starting point, then that length will be L. This curved distance I will call A, which stands for arc length. So the curved distance along the ground, I think, is a particularly useful one because if you actually were to drive the distance, for example, you would get out there, drive, and measure the distance with the odometer in a car. What you would be measuring is, of course, the arc length. And Google Maps, Google Earth, that's what they will be giving you. They will be giving you the ground trace, the distance along the ground. And that's why I'm going to start with that. I think that that's the best way to measure the distance along the ground, is because anyone in these conversations, the most common go-to for measuring distances between places is Google Earth. And then down here, C, if you just draw a straight line between those 2 points, as if you were maybe able to somehow shoot a laser beam from there to there, I mean, it would be going through the ground in this model, but the straight line distance, I'll call that C for chord length. So because your go-to in flat Earth discussions is Google Earth, and Google Earth gives you that arc length, let's derive H. We're looking for H in terms of this arc length here. So to begin with, I'm going to express the angle inside here, the angle that we are going through, the fraction of the circle that we traverse is the angle alpha. And the radius of the Earth we will call r. The radius times the angle swept will give you the arc length. Now that's if the alpha is in radians, right? If the angle is in radians, then you simply multiply times the radius of that circle and you'll get the arc length. That's why we like radians. We like radians because it works that way. And from that, all I have to do is a little algebra, and now I know alpha is just the arc length divided by the radius, and I'm going to want to keep that around. I'm going to pin that. All right, so let's take a look at these two corners here. I think you can see that these angles are the same, and let's call those angles beta. And because we know that the three angles, the internal angles of a triangle must add to 180 degrees, and we're working in radians, so that is pi radians. So 2 b's plus 1 alpha, 2 betas plus 1 alpha must add up to pi, and that gives us beta is pi over 2 minus 1/2 alpha. Okay, how about this angle right in here? Let's call it gamma. This, I think you can see, is a right angle. And so beta plus gamma must add up to pi over 2, making gamma pi over 2 minus beta. And if beta, we can just fill in beta here. It was that. And we can see now that gamma is 1/2 alpha. So that's pretty convenient. This gamma angle here, which is the angle down. This is the angle we're looking downward if we're going to look at the end point. That angle is exactly half of this angle, and that will be convenient. Let's fill in what we know alpha to be from over here, and we will get, in terms of the original numbers, gamma is the arc length divided by twice the radius. And I think that we'll want to keep that around. So we'll just stick both of those up here as we continue working our way towards what is h. This is what we're going for. So what are we going to do next? How about this chord length here? Remember chord length? I said I was going to call it C. I just went and looked this up. It's actually fairly easy to prove and derive where this comes from, but for reasons we're going to see in a bit, it's not really worth the time. The chord length can be given by twice the radius times the sine of half of that internal angle there. That'll give you the chord length. And alpha over 2, of course, that's gamma, right? We had that. And gamma, we can put in the original numbers there for gamma, and we'll get that the chord length is 2 times the radius times the sine of the arc length divided by twice the radius. So we'll save those here. We'll be using those now. Next up, I am going to notice that I have a right triangle right here. The angle here is gamma, the hypotenuse is C, and the opposite is H. Opposite over hypotenuse, that's the sine of the angle. So there we go, we'll plug that in. Let's rearrange because we are trying to solve for H. So H is just C times the sine of gamma. What is C? It's right over here. Let's fill that in. Boom. And gamma, I think we have gamma as well. Here's gamma. Let's fill that in. And look at that. We have H equals 2R sine of this times sine of this again. Or let's just simplify 2R sine squared arc length divided by 2 radius. And there it is. There is our final equation. If you were given the actual arc length and the radius of the sphere you want to test against, then the drop amount can be given by this equation. Some of you out there are going to be familiar with the equation for this, and you might say, that ain't it. That's not the equation. And in fact, the first thing I did when I derived this equation was I went over to Metabunk and I checked it. And I was a bit stymied to discover that is not what Metabunk uses for their drop distance. It turns out that my logic of using the arc length to base this is not the same decision that everyone else has made. you can presume that the distance we are talking about is a different distance from that, and it seems that many people have done exactly that. You might have been expecting to see a cosine here instead of a sine squared, and let's take a look at exactly where that comes from. We could instead base it on this horizontal length L. Now at this point I'm going to link it up in the corner right there. Pop! AB Science does a fantastic video on the 8 inches per mile squared approximation and how that was derived, how the approximation was derived. And he derives it from this version here where we are given L, the length across the top, as opposed to the one that I did where we were given the arc length. So let's derive that now, and he derives it in a slightly different way than what I did. So I will follow along right here with his method, and I will therefore get the exact same result that he got, and then we'll come back and compare. The first step is to realize that this L here is the same as the L across the top, and that gives us this convenient little right triangle right here. There's a right angle here, so we have a right triangle. We call this internal angle alpha. Then opposite over hypotenuse is the sine of the angle again. So that's right there. And if we want to solve that for the angle, we will just take the arc sine or inverse sine. So we now have the angle alpha. Let's call the adjacent here, the adjacent side of this right triangle, let's just call that B, maybe for base. Maybe B stands for base. So we have, this is the adjacent. And what do we know about the adjacent? Of course, that's the cosine. So the adjacent side, B, is our cosine of alpha. Remember that the entire length, all the way to the tip top here, that was the radius, R. And of course, our little adjacent here is B. And that tells us that H here, H is this distance, and so H plus B equals R. Write that down. Okay, where do we go next? Well, we're gonna want H, of course. So we'll just do a little rearrange, and we have H equals R minus B. All right, but we know what B is, so let's fill that in. H equals R minus R cos alpha. And we know what alpha is, so let's fill that in. H equals R minus R cos inverse sine of L over R. And that's where AB Science leaves it. I'll go ahead and just pull out the R just because I like the 1 minus cos. But let's highlight this equation. This is our final equation for the actual drop rate based on that horizontal distance. It's a little uglier. I think it's a little uglier than the one I had. But the most notable thing that I found right away, and I was a little troubled by, is that this one is a 1 minus cosine, whereas mine was sine squared. Why do we have different equations? This is my equation. This is AB Science's form, and where I have just put in the alpha. We both based it on deriving alpha first, and then worked it in different ways from there. I used the chord length, and I got 2r sine squared of alpha. And AB Science used the trick of recognizing this right triangle, and he ended up with an entirely different equation. Now, if we put the same alpha in, I should really stress, if we put in the same alpha, we must get the same result. But we have different equations. So this is a really great moment for any people out there, particularly those who do not trust math, to listen to me as I explain the following sentence. If the math is correct, these two values must be identical. They must be exactly the same. It's kind of like saying 3 plus 3 plus 3 must equal 3 times 3. And we know that it does. It must equal 3 squared. And we know that it does, right? 3 plus 3 plus 3 is 9. 3 times 3 is 9, because 3 times 3 is, by definition, 3 plus 3 plus 3. That's how it works. In math, there are often multiple ways to arrive at your answer. But if the math is correct, they must arrive at the same answer. That's how we know that the math is correct. Let me say that again. If the math does not arrive at the same answer, then you know for a fact that the math is not correct. If you've gone along in a different journey through your math and arrived at different looking equations, as long as there are no mistakes, those different looking equations must have the exact same value. And in fact, they do. You can go and look up a trigonometric identity and find one exactly for this. I won't go through a table of trig identities, but essentially we just proved this particular one with this by solving this equation in these two different ways. These are in fact identical statements. So this is just a style question now. Which one do you think looks prettier, is more convenient to use in your spreadsheets? You can choose either one. They're equivalent. Because I like the elegance of this most recent derivation where we used the right triangle and did not involve the chord, I will go with this one from here on out. And we will find that in all of these different derivations that I'm doing, I've done 2 now, I will always be searching for the alpha, and then once I get the alpha, I'm going to just plug it right in here. So now that I have done this part, I don't have to repeat it. All I have to do is just get alpha, and I'm ready to rock. Okay, let's get to it. There are 2 more I promised I'll show you. So what's next? The next one I want to show is the one that I think is the equation used by Metabunk. I went and looked at the Metabunk curve calculator because I wanted to show and compare my results to their results. And from what I saw of the diagrams and my quick perusal of the discussions, I believe Metabunk's curve calculator bases its distance, its horizontal distance, on this line D, which I'm calling like a peak-to-peak kind of a view. As if you're looking at a mountain. If there was a mountain peak here, if this was a mountain here, then it would be tilted away from you somewhat. And any flat earthers who happen to be watching to this point, yes, that mountain or that tower or that tree is tilted away from you. I did say it. It is. It is tilted by exactly this angle alpha. And when you do the numbers, you're going to find that alpha is a very, very small number. And that's why it doesn't look like it's tilted away from you. But I digress. What we have here is just a right triangle. And we have the opposite and we have the adjacent. So we can just get the angle with a tangent. Tangent of alpha is the opposite divided by the adjacent. And so if we want alpha, we will do arctangent or inverse tangent. And we got that. Now that we have alpha, as I mentioned, we can just plug that into our previous equation. And I'm using the cosine one. So we'll plug that straight in for alpha. And we have our final equation. And if anyone happens to know whether Metabunk actually uses this equation or not, I could have dug into the source and found out. This is what I got based on perusing the diagrams and the discussions pretty quickly. I don't want to spend that much time on it. One more version I'll do just for the lulz is let's base one on the chord length. Let's imagine that the distance here, the distance given is this chord length I've called C. I have heard people say, oh yes, but you have to use chord length. And so because of that, let's do one with chord length. The chord, as I showed before, is just 2r sine of alpha over 2. So if we had alpha, then we could get the chord length. But no, this time we have the chord length and we have to get alpha. So We'll just rearrange to get everything except for the alpha over there. And then we're going to need an arc sine, an inverse sine, to strip that away, and we will now have alpha. There we go. We solved for alpha, as we did with all of the other versions, based on the given values that we had. So now we have alpha. We will just plug it into this same equation as before, plug that straight in, and we'll get this lovely equation that is different than anything we've seen before. And that gives us this lovely equation here. So there you have it. I have now derived 4 different versions of the drop equation, and it depends on what you considered the input distance to be. Okay, so that's it for the math. Let's now hit to the punchline. Finally, the big reveal. How do these equations compare to the 8 inches per mile squared estimate? I've got the distances in miles because the equation is in inches and miles. So I'll have the distances in miles here, and all of the drop distances I have written in feet. Don't get confused. Even though it says inches here, inches are going to get pretty big as we go out into the distance, so I chose to show it in feet. If you're 1 mile away, the 8 inches per mile squared will give you 8 inches. And that comes out to 2/3 of a foot. So that's that. How does that compare to our actual values? Here's the actual amount of drop distance according to these different equations. And we can see that's super close. I mean, that's within tiny fractions of a distance. And so at 1 mile, it's fine. How far? Let's go 5 miles. We'll go at 5 miles. And we'll see these are the real world numbers, and here's the approximation. That's still pretty darn good. It's, 100th of a foot is how far off that is. At 10 miles, the drop is still pretty good. Look at that. So it holds out to 10 miles. So that's good. But what if we're doing like a longer observation? We're going to go out further. Let's go out to 50 miles. So out at 50 miles, the actual value is there, and depending on which method you use, it's off by about a foot, or not even a foot, half a foot. From this one, based on arc length, which is my favorite, I'm off by like half a foot. I'm off half a foot over 50 miles. I'm going to say that's a pretty good estimate. If 50 miles away, you're only off by half a foot, that's pretty good. I'll accept that. Okay, let's push it now. Let's push it out to 100 miles. Surely this approximation is no good at 100 miles. Here we go. The actual value, 6,668 feet. And the estimated value, 6,667 feet. We are now off by, oh my gosh, it's over a foot. It's over a foot wrong at 100 miles. At 100 miles, it's off by a foot. That is a darn good estimate. So, yeah, if somebody is telling you that estimate only holds over short distances, I'm going to have to give you a bit of a pause on that. That estimate is shockingly good. Okay, but that's still only 100 miles. Let's go nuts. Let's just go crazy. Let's take it out to 1,000 miles. At 1,000 miles, here's our estimate based on 8 inches per mile squared. And here are our actual values depending on how we sliced it. I think you'll find that's still pretty decent. How decent is it? I've made a little chart. Let's cut away to that now, and I will show a graph of what we found as well as percent errors now. So here is a Google spreadsheet, and I will make this publicly available to anybody who wants to look at it. I'll put it down in the description. And you can check it out and see if I've made any kind of mistakes in here and check my work. So here I have those 4 different calculation methods, and you can see the equations right there. And here I have the 8 inches per mile squared estimate. Notice that the division by 12, so this is in feet. All of these are in feet. In this column, column G, I am showing the error, the amount of difference between F6 and B6. So I'm comparing against arc length, my chosen method. If you think you want to use one of these others, you think it's better to use the peak-to-peak version or the horizontal version, then you'd have to change that. And then in the last column, I have the error expressed as a percent. And yeah, there's division by 0 because there's no error here. Or rather, the value is 0. As a percentile. So this means 0.03%. And a negative number will mean that the value is low. So that's just what that means. So this tells you how good approximately your approximation is as a percentile value. So next up, over here on the right, I've made us a nice little curve that shows a comparison of these 5 different methods of estimating the amount of drop. And we'll see our 8 inches per mile squared sitting right in here in between the peak-to-peak version and the horizontal length version on the extreme ends there. And all the way out to 1,000 miles, this is a pretty good approximation. Okay, but yeah, 1,000 miles, maybe that's not far enough. Let's push it. Let's see what happens if we just go all out. And this is what we get. Interesting thing for me here is that the horizontal length method and the arc length method diverge by more than the arc length method does against the 8 inches per mile squared method. The takeaway here that was absolutely eye-opening for me is that the 8 inches per mile squared estimate is really, really good. How good is it? How good is it? So I might want to ask the question, how far out do you have to go before your error becomes 1%? It's like at this point we're at fractions of a percent of error. How far out can we go and still stay under 1%? So let's scroll down as the numbers increase to right here. The first time the number reaches a 1% error is at a distance of 1,400 miles. So this 8 inches per mile squared approximation is good to within 1% accuracy out to 1,300 miles and beyond. So that may sound a bit shocking, but there you go. That's the actual numbers. And I invite you to check it yourself and see if that isn't correct. Finally, that brings me to the last point that I wanted to make tonight. And that is, why am I talking about this? Why is this so important? Obviously, I think this is really enlightening. The comparison is so accurate. It is far more accurate than I ever anticipated. And I want to stress that because I have seen numerous different flat earth debunkers, so that's globers who specifically go out to debunk the myths of flat earth. And I have heard them say that 8 inches per mile squared is an approximation over short distances. And they have stressed that. And they say that 8 inches per mile squared is a parabola, not a sphere. That's a parabola, not a circle. It can't be right. It's definitely wrong. I've heard that many, many times. And I am telling you, if you are a debunker, if you're in the business of dunking on the flat earthers, it's time to be humble. It's time to accept check your values and realize that, no, this is a damn good approximation and it holds out to 1,000 miles. So it's perfectly fine. If somebody wants to use 8 inches per mile squared, that's fine if they're using it correctly. Let me stress, before we go in anymore, let me say this. The problem that we encounter with flat earthers using 8 inches per mile squared is that the equation has nowhere in it to account for the viewer's height. The viewer's elevation is not in that equation, therefore it cannot account for the viewer's elevation. Therefore, we do not use it to calculate the hidden amount. The amount of a mountain that is below the earth cannot be approximated with 8 inches per mile squared. 8 inches per mile squared is only good for calculating the drop distance. And if you're a flat earther out there listening, I hear you in my head saying, what's the difference? It's the same. No, it is not the same. It is not the same. That's a separate topic we'll discuss maybe some other time. But hidden distance and drop distance are not the same amount. So, globe defenders and debunkers, don't say that's a parabola. I don't want to hear you say that anymore. That is not a valid argument against this approximation. The approximation is fantastic if you are talking about drop height. The fact is, we are very rarely talking about drop height. We are almost always talking about hidden amount. If we're talking about hidden amount, 8 inches per mile squared is no good. If we're talking about drop height, it's fine. Okay, so where I really want to double down on this discussion is to highlight a comment thread that occurred on my own channel. I have blacked out the name of the individual here because I do not want this to be some kind of calling you out. I do not want this to be me being a jerk or just trying to win in an argument. I am highlighting this because this describes really what has become the central theme of my channel. The central theme of my channel is that the flat earth versus globe earth discussion has long ago left reality behind and become a matter of us versus them. And we're going to illustrate this by looking at a glober who ultimately will begin attacking me because I refuse to support his attacks on flat earth. All right, so if you are this individual, your comments are still there. Of course, I'm not deleting your comments. You're welcome to, I invite you to respond to this if you wish and say your side of the story. And by all means, if I have made the mistake, if I am incorrect with any of this, please, please correct me. That is what this is all about. It's all about holding ourselves to a higher standard. So when we make mistakes, I expect you to correct them. So here we go. Let's take a look and analyze a little bit of this comment. We start with the repetition that the 8 inches per mile squared is an approximation over short distances. We sometimes hear the flat earthers accuse us of just repeating a mantra or reading from a script. Look at this. That's exactly what's happening here. This is not a true statement. As we just saw, I just showed this is an approximation that's good to 1,000 miles. In no way is that good over only short distances. And yet this person is just repeating that. And I have heard well-known, very highly regarded debunkers who have repeated this exact same statement. And I want to stress to them, I'm not calling you out by name. I have tremendous respect for you and the work that you did. But hey, you made a mistake. It'd be awesome if you'd go and correct that. Okay, What else will I point out here? This individual is claiming that it was not properly squared, that for some reason he thinks somebody is using the equation as 8 inches per mile rather than 8 inches per mile squared. And yeah, that confused the heck out of me, but that is what he said. And he then further explained that you'd have 2.8 inches for 1 mile rather than the 8 that I had calculated. So that confused me a lot, and my response was that I was confused, but then he repeats 8 inches per mile with no square. And so, and honestly, nobody can say that 8 inches per mile is a reasonable approximation, and that would be correct. Yeah, you cannot say that. 8 inches per mile is no good. That's no good to anybody. It's 8 inches per mile squared. You have to take, I say this, you have to take the distance and then you square that distance and then you multiply that by 8. And I point out AB Science's video and that you should do that. And I suggested just make a spreadsheet as you saw that I have now done and published as well. And then I go on to explain the difference between hidden height and drop height is really what we should be focusing on, not whether 8 inches per mile squared is okay. But what is the answer? Again, 8 inches per mile with no square. He says it again, and then I ask, without the square, who is doing that? I'm confused. I've never seen anyone make that mistake. That would be a tremendous mistake, of course. And we discover he thinks that I have done that. You said in a mile, the globe is supposed to have an 8-inch drop. That's 8 inches per mile with no square. It is 8 inches per mile with no square, but it's also 8 inches per mile with the square because 1 squared is 1. So, yeah, what does he go on? He goes on to say, the drop for 1 mile, you have to take the square root of 8. And that's where he's gotten the 2.8 inches drop at 1 mile distance. Now let me reiterate, this person here is a glober. This is a globe believer who, in my opinion here, according to my analysis, this person has made a mistake with the math and just needs to be corrected. I hold the globers to a higher standard. I expect you to accept the correction as I do myself. When I make a mistake, it's time to make the correction. This is not correct. So I explain in great detail, as I have just done in this video, 1 mile, 1 squared times 8, that's 8 inches. It's not 2.8 inches. And then I popped over to the Metabunk curve calculator and I punched in some distances, and this is what I got. Okay, and then I went on to say, you know, there's different ways to measure it and stuff. At that point, I checked it out to 500 miles, and it was still within less than 1%. So I think that's a pretty darn good equation. Once again, stressing, watch out for them using it wrong. Now, I pointed out Metabunk's curve calculator. That'll be interesting on the next slide. And also this line here, I do want to stress that I think this is where the whole conversation maybe went off the rails. It feels like it was kind of already off the rails, but I think it definitely went off the rails when perhaps my mistake, I should not have written it this way, but I said, to sum it up, don't try to dunk on flat earthers by telling them 8 inches per mile squared is wrong, but do watch out for them using it wrong. I stand by this statement, but perhaps it sounds, is worded badly, a little too aggressive maybe. But yes, please stop trying to dunk on flat earthers with false statements. 8 inches per mile squared is a fantastic, it's a surprisingly accurate estimate for the drop distance over extreme distances. But the problem is that flat earthers use it for everything, even when it doesn't apply. And usually it doesn't apply. But what was the response? Here the response was that he had not made any mistakes. He insists he is correct still after I went to all that effort. And furthermore, the reason I have done this video showing all of this math is because he accuses me of being unable to do the math. Please do go and review that math, and if you find any mistakes, please correct me. We all make mistakes. And then finally, this one, which honestly kind of makes me chuckle, is that I found a website that confirms my bias. The website you'll recall that confirms my bias is the Metabunk Curve Calculator. So I'm still under the impression that this individual is a glober. I think this is a glober here who is trying to attack me for using Metabunk Curve Calculator to confirm my bias against his math. And so then I try to, reset the conversation because I don't mean to be offensive. I don't mean to be argumentative here. I'm just trying to get to the truth. And then normally a comment like this, like if a flat earther or a glober just comes out and calls me an asshole or calls anybody an asshole on my channel, normally I delete it. I have left it because of this conversation and how it brings me into this video and the extreme importance of this topic. I found a flaw in what I thought was a flat earther's math, but it turns out it was your error and you won't own up to it. This is your problem. I solved my side of it. And I tried one more time with over a distance of 1 mile. I came up with 8-inch drop. Is that incorrect? What is the correct value? I don't know how I could be any more friendly about it than that, but alas, this individual has not returned. So I think we may have seen the last of this person unless he chooses to respond to this. If you know who this is and you forward him the video, I expect, let me address you now. I expect you will be rather angry about this. I understand. You have a right to those feelings. Those are valid feelings. You could be angry at me, but please take a moment, take a deep breath, step away from it for several hours at least before you come back. And then when you do, come back and comment. And I would invite you to consult with your friends in the Globe Earth community. Consult with them and check, was perhaps your statement incorrect? Maybe you made a mistake, and maybe the appropriate course of action would be to correct the mistake at this point. I am happy to accept that at any time. So if I may sum up this entire conversation, the main points are 8 inches per mile squared is surprisingly and a very accurate representation of the amount of drop you get as you travel along a distance. If you're measuring your distance as the arc length, as the length along the ground, then the distance of drop between a straight flat plane and that spherical Earth is in fact very, very close to 8 inches per mile squared, and it holds over a very long distance. So I'm actually going to give that a solid win for the flat Earth folks for having an equation that I did not believe would work, and I have seen numerous flat Earth debunkers say was not accurate and laugh at the flat earthers for using it. It turns out that's really good. That's fantastic in my opinion. So win one for the flat earthers. And this brings me to the real lesson here, which is it's not about having to win. I don't have to win. You don't have to win. It's not a competition. What we want to get is that we both be correct. If we can just have a respectful conversation where we go through it and we make a spreadsheet and we derive the equation and we check our math and we double check our math and we show it and we discover the actual facts, then we can both walk away smarter than we were yesterday. And that's what we're trying to achieve. We don't have to have a winner and a loser. We can both win if we both walk away knowing something more than we had yesterday. And so for the Flat Earth Debunkers in particular, I know some of you make a living by dunking on the Flat Earthers, but I'm going to continue to hold you to that higher standard. It's not okay to just run a Jerry Springer show where you have a dumpster fire every week for entertainment purposes. You are out there representing science, you're out there representing truth. And so, you know, it'd be really nice if you treated other people with respect. I can't demand that of you. But what I really do expect out of you is that you say truthful statements yourself and not go out there spreading things that are just not accurate and using that to mock others. Nothing could be more ironic than that. And it gives us all a bad name. So corrections may be in order out there, and certainly correct your scripts. Let's not say 8 inches per mile squared is a parabola. Let's not hear that anymore. That is now an outdated statement that you know better, right? So thanks, everybody. Hope to see some lively but respectful comments on this one. Okay, good night.